All right, everybody. Welcome to the little mini lecture that's going to make up for some of the time we lost last week by giving the test and giving the practice test and such. This is the beginning of Chapter 4, and Chapter 4 is on the historical development of astronomy as a science. Really, the history of astronomy is probably not a good title for this. It's more on how astronomy developed as a science. And as I mentioned at the beginning of the class, I think this is a very important thing, especially for most of you who are not going to be science majors, because it's important for you as citizens to really understand how science works. That it's not a beeline to the truth, and that it's based on evidence, and sometimes the ideas that work at some point are overthrown and shown to be wrong, and we get better evidence that shows other ways of describing things. But science generally gets it right in the end and generally self-corrects itself. Now, we could go back all the way to Stonehenge. We could go back to the ancient Babylonians, who were skilled sky watchers. But we generally start with the ancient Greeks. And the reason we start with the ancient Greeks, and we've talked a little bit about them already, is because they were the first astronomers to, they were the first scientists to devise a physical model of the universe. Okay, and a physical model, a physical model is absolutely essential to modern science. Let me just see if I can describe what a physical model is to you. A physical model is not a model made out of, plastic and airplane glue or balsa wood or something like that. It is a mental model that uses oftentimes mathematics to describe how things work and to also predict when things will happen. So a physical model is something that both explains why something happens, but also predicts when something will happen. In the case of astronomy, it would predict when Mars would be retrograding, for example, or when Mars and Jupiter would approach each other in the sky, and explains why that happens as well. A couple of examples of his physical model would be, you probably have heard on the weather forecast, that they have various meteorological models in predicting how bad a storm will be and what its track will be, how it will develop over time. That's a physical model. Another very simplistic physical model you probably remember from middle school is the solar system or Bohr model of the atom, where the atom is basically like a little teeny tiny solar system, where the nucleus is like the sun and the electrons are like little planets whirring around it, and like little tiny planets going around the sun. Not only is the atom much, much smaller than the solar system, but it's also held together with a different force of nature. It's not held together with gravity like the Earth is held to the sun. It's held together with the electrostatic force, which we'll also talk about again a little bit later on in the course. Okay, so let's start with some influential Greek natural philosophers. Okay, natural philosophy was what basically physical sciences were called, even up to as recently as a century ago. Natural philosophy was considered to be the physical sciences. Natural history was considered to be like the biological sciences. And we start out with the philosopher Plato. Now, Plato came up with one very important and simple idea. Was he thought that it was important to use uniform circular motion to describe the heavens. Okay, it seemed like, as we saw earlier in the semester, that everything went around the Earth in a big circle. Well, the sun would rise in the east and go in a semicircle across the sky and set in the west every single day. Same thing with the stars. The stars would make circles around the North Star every night. And the planets would also going around in a circular path, although their motion was a little more complicated. So the ancient Greeks were really into geometry. They basically invented our ideas of modern geometry. They discovered the number pi, for example. And so Plato thought that what would be better to describe the perfection of the heavens than the perfect form of the circle, and that the motion should be uniform. It shouldn't be haphazard. It shouldn't speed up or slow down. It should go around at a constant rate. Okay. We also talked a little bit about Aristotle in the past, where he separated the earthly realms and the heavenly realm. He said Earth was where things were haphazard, unpredictable. The heavens were perfect and permanent and changeless. When they did change, they were changeable in a very predictable and ideal way. He also said that they were made of different stuff. Okay, one of the reasons the heavens were perfect was they were made of a different substance than the earth. The earth was made of the four elements of nature: earth, air, fire, and water. Okay, now we think of this today as like, oh, he wasn't very smart. There's oxygen and nitrogen and hydrogen and helium and all those are the elements. Well, he wasn't really talking about the elements, even though he called them elements. What he really meant was that there were four states of matter, and that he got perfectly right. Okay, there's solids, that would be earth. Okay, earth is a solid. There's liquids, that would be water. There's gases, that would be air. And there's a fourth state of matter you might not be so familiar with, and that's a plasma, an ionized gas like a candle flame, and that would be fire. Okay, so fire is an ionized gas. So we got the states of matter absolutely correct. Now the heavens were made of another state of matter, and since the heavens were perfect, it was a fifth substance, the fifth essence as he called it, or quintessence. And it was this perfect crystalline substance, so there were these crystal spheres out there that held the planets and the sun and the moon and even the stars. And they thought that it was a real thing. Okay, and this stuff quintessence, we still use the word quintessence, like quintessential, to mean something that's perfect. You know, the quintessential entertainer, the quintessential actor, the quintessential athlete would be somebody who's the ideal of that genre. So the heavens were composed of these nested crystalline spheres made of a perfect substance, quintessence, that rotated naturally. There was no force required, and that's what the heavens were made out of. Now, the ancient Greeks not only knew that the earth was round, they did not believe in a flat earth, but they also figured out the size of it, and we'll tell you that on the next page of notes. Okay, it was round, but it was stationary. Okay, so we had a round earth stationary at the center of the universe, and surrounding it were various spheres, the outermost of which was the celestial sphere. They didn't think the celestial sphere was a fictitious thing. They thought it was a real thing, that the stars were like little Christmas lights pasted up on this black velvet interior of a globe that went around us every day. Okay, now why would they think that the earth was stationary? Well, common sense for one thing. First of all, you don't feel any motion when you're on the earth. Still today, we don't feel any motion. Okay, so back then there was no such thing as a smooth ride. If you moved anywhere, you knew that you were moving. But when the earth moves, you just don't feel it. Okay. Also, if that didn't convince you and you said, well, maybe it's just too big, we don't feel the motion, Aristotle would have said, well, then why, when I drop my notebook, does it fall straight down? Why doesn't it fall off to the west if the earth is moving to the east? Let's say you said the earth is turning. Well, then why do objects fall straight down? The earth doesn't turn underneath them. Well, that was a good piece of observation that seemed to suggest that, yeah, you're probably right, the earth doesn't move. Okay, we'll address that a little bit later in the chapter when we talk about Galileo. Okay, also, if the earth was moving around the sun, if you said, well, the earth is going around the sun once a year, that's why the sun seems to go around the zodiac, for example, Aristotle would have said, well, then why, when we're on one side of the sun, don't the constellations look larger, and we're on the other side, they don't look smaller? Why isn't this thing called parallax? The word parallax means a shift in the position of an object caused by the observer's change in motion. When I go to one side of a room, the students I see on one side of the room are the same students, but they seem to be arranged differently in my line of sight than if I go to the other side of the room. That should happen if the earth goes around the sun. Remember, they believed in a cozy little universe back then, so if you said that the earth went around the sun, the stars ought to move. They should shift position due to the earth's motion. But there was no stellar parallax observed. And so that was evidence for a stationary earth. So it seemed like, game, set, match, the earth doesn't seem to move. Okay. However, this didn't stop a couple of radicals from coming up with crazy ideas. Okay. Two of them were named Eratosthenes and Aristarchus. They just don't make names like that anymore. They had these radical ideas that the earth rotates on its axis once a day, and that causes the rising and setting of the sun, and it orbits the sun once each year. And that's what causes the motion of the sun around the zodiac and things like that. Well, did their ideas become very successful? Not really. They had their followers, but unfortunately they were a little bit too far ahead of their time. However, Eratosthenes is best known for something that he did. He measured the size of the earth about 100 BC. Okay. What he did was he realized, he lived in the town of Alexandria, which was on the northern coast of Africa. That was a colony. It was in Egypt, actually. It was a colony of the Greek Empire at that point. And it's about the same latitude as, say, South Carolina or Savannah, Georgia. So it's farther south than we are, but it's not anywhere near the equator. So the sun does not get to be directly overhead at Alexandria. However, he heard that on one day of the year, there was a town in southern Egypt called Siena, where the sun did go directly overhead and would shine down to the depths of a deep well. And so he realized that this is because the Earth is curved. Okay, it's something like this. If I can draw here the, let's see if I can draw the North Pole and the South Pole. Okay, this would be like on the summer solstice. There's the North Pole. There's the equator, there's the South Pole, and the sun's rays are coming in from the right, parallel, because the sun is very, very far away. And so from Alexandria, if you put a stick in the sand, it'll cast a 7-degree shadow. In Siena, well, Siena is near the what we call the Tropic of Cancer, which is the 23.5 degrees above the equator. Okay, 23.5 degrees above the equator, and there's no shadow there. The sun would be directly overhead at noon. Well, Eratosthenes said that, look, if you could extend these sticks to the center of the Earth, they would make this sort of 7-degree wide slice of pizza. Okay? And so that means that the distance from Alexandria, if you multiply it by how many slices of pizza you got to make the whole Earth, well then you could get the circumference of the Earth. Now, problem was he didn't know the distance between Alexandria and Syene, so he actually hired some poor slob to pace off the distance between these two places. Apparently he did a very good job of it, because when he found out what the distance was here between Alexandria and Siena, he just multiplied that by the number of slices, which happens to be, divide 7 degrees into 360 degrees, you get 51.5 slices. So 51.5 times the distance between Alexandria and Siena should be the circumference of the Earth. Okay? The Earth's circumference is 51.5 times that distance. He missed the actual circumference of the Earth by only 5%, which was absolutely amazing for that time. Unfortunately, his discovery and his works were destroyed when the Library of Alexandria got destroyed in an invasion, and it got lost to antiquity, to history. We only know of it now because of secondary writings that told of Eratosthenes' discovery. Also, ironically, it turns out that if Columbus, for example, knew of his measurement and accepted his measurement, he never would have, quote-unquote, discovered America, because Columbus thought that the Earth was about half the size that it was. So when he went across the Atlantic and bumped into North America on his way to India, he was trying to find a shorter trade route to India, and if he knew that the Earth was as big as it was, he never would have bothered. He would have said, that's ridiculous, I'll just go the old-fashioned way. So, ironically, if he had known a measurement that was done well over 1,000 years before he lived, he wouldn't have been famous probably today. We certainly wouldn't have Columbus Day. Problem with these two guys, Eratosthenes and Aristarchus, they were a little bit too far ahead of their time. One of the things we're going to learn in this chapter is that life, a lot of life is good timing, and these guys had bad timing. They were absolutely right. But Copernicus gets credit for coming up with this idea of the moving Earth and or the Earth orbiting the sun and rotating as it goes around. Okay, they also couldn't disprove Aristotle's teachings, which was the main problem. They had no way of disproving or proving that the Earth moved, or having evidence that the Earth moved. And so, although they had their followers, their ideas never caught on in a great, large way, a big way, and so they were kind of lost to history.